Welcome to the ICS Friday seminar. Today we're going to have Sebastian Trujillo-Gomez. I hope I said that correctly. Sebastian was a PhD student in New Mexico, working with Anatoly Klipin. And after that, he moved here to Zurich, to the ICS, and he did a postdoc working on dwarf galaxies. And now he is in Heidelberg, working on even smaller things, globular clusters mainly, and star formation. And I'm very happy to have him back here and hear what he has been up to over the last few years. So welcome, Sebastian.
Thank you. And thanks also to the organizers for inviting me. I'm super excited to be here again after so many years and to see so many familiar faces from when I was working here. So yeah, even though I'm working on small things like star clusters, the idea here is to go across all the scales, from star clusters to galaxies to the nature of dark matter. And so the general theme of the talk today, I'm going to talk about 3 projects, but they're all connected by this general theme of how a better understanding of the detailed physics of star and star cluster formation can allow us to really go back in time and piece together, reconstruct the assembly histories of galaxies and put constraints on the physics of galaxy formation and possibly even the nature of dark matter. And here in the background, you can see a simulation that I will be talking about today. This is a simulation that models the formation and evolution of galaxies and their star cluster populations. As you can see, the galaxy is a Milky Way mass galaxy forming in the background, and the globular clusters are colored dots, colored by metallicity. And so you can see already how much information is encoded in the properties of the globular cluster system of a galaxy like the Milky Way. And this is what the talk will be about today. So like I said, I'm going to be talking about 3 different projects or 3 different ways of going back in time. In the first one, I'll discuss how we can reconstruct the assembly of the Milky Way galaxy using the kinematics of its globular clusters as measured by Gaia. And the second one, I'll talk about how understanding the impact of galactic environment on star cluster formation allow us to understand why this new class of galaxies, these ultra diffuse galaxies, seem to be so good at forming globular clusters. And in the last one, I'll tie this overabundance of globular clusters to galaxy formation and to the emergence, how they influence the emergence of UDGs. So let's start here in our own galaxy, in the Milky Way. Of course, the question of how the Milky Way formed is central to the field of astrophysics, and it's a very old question. However, real progress only came in the 1960s and 70s. In 1962, again, Lindenbell and Sandage wrote this seminal paper where they looked at the orbits of stars around the sun as a function of their ages, and they looked at their orbits, and they found this very clear correlation between ages and orbits, where older stars have larger orbital eccentricities, also lower angular momentum, and larger vertical velocities compared to younger stars. So older stars are kinematically hotter. And from this, they concluded that this is archaeological evidence of the collapse of the Milky Way galaxy. This is the first time that this was seen, and that the data require that the older stars form out of gas that was falling towards the galactic center in the radial direction and collapsing from the halo onto the plane of the galaxy. And presumably the younger stars formed out of a rotationally supported disk. So they have very distinct kinematics. And so you can see how such a simple observation already has a lot of power to piece together the assembly of the galaxy. Later on in 1978, Searle and Sin looked at the globular clusters of the Milky Way. They also looked at their ages and metallicities as a function of galactocentric distance. And they found that the inner globulars have very small age spreads at fixed metallicity, whereas out in the halo, they have a large H-splits, including relatively young globular clusters. And so they interpreted this as evidence that the clusters in the outer halo originated in protogalactic fragments that continued to fall into the Milky Way to accrete after the central galaxy had already formed. And you can see how this, again, is quite a powerful observation. And now, of course, this was pre-lambda CDM. Now that we have the cosmological interpretation, we know that this is a natural consequence of the hierarchical assembly of dark matter halos and the galaxies they host. These are simply satellite galaxies that form their own stars and continue to form their globular clusters as they continue to fall into the Milky Way. So in this way, we can probe all the galactic progenitors of the galaxy. So in the last 3 years, the Gaia satellite completely revolutionized the field of galactic archaeology. Many studies came out of this, and we are up to about 10 galactic progenitors, or the order of 10 galactic progenitors identified in the stellar debris that has been observed by Gaia, including the Gaia sausage, Kraken, and many others. And so we know that stars are very powerful tracers of the assembly of the galaxy. So this led us to ask ourselves these 3 questions. Can we use the kinematics of the globulars around the Milky Way to understand how globular clusters form? Second, what is the best observable tracer of the assembly process? And third, are globulars better tracers of galaxy formation than field stars? So these are the 3 questions that we wanted to answer in this study. But of course, why should we bother with globular clusters? What's the difference between them and stars? Well, they're much brighter than stars, so observationally, they're easier to study at much larger distances, even cosmological distances. Second, their phase mixing time is much longer than for satellites, so they stick around for much longer. So they can trace, excuse me, so they can trace earlier mergers. And the most important is that they have more dwarf galaxies have more globular clusters per unit stellar mass than more massive galaxies. And you can see this in this empirical observation. This is the famous globular cluster system mass halo mass relation. And it expressed as a ratio, you can see that across the entire galaxy mass range, galaxies have a fixed fraction of their halo mass, excuse me, a fixed fraction of their halo mass in their globular clusters. So if I compare this to the stars, you can see that they drop off quite rapidly. In this sense, dwarf galaxies have more globular clusters per unit stellar mass than massive galaxies, and therefore we can trace lower mass mergers. But of course, first we need to understand how globular clusters form and evolve. And this has been a matter of debate for several decades, with many models proposed, some of which are propose very exotic mechanisms for their formation. But for this, now we have these simulations that our team has been working on for quite a few years. These are the E-mosaic simulations that attempt to model the formation and coevolution of star clusters and galaxies in a cosmological context for the first time. These are a first set of 25 cosmological zoom-ins of Milky Way mass galaxies. They use the Eagle galaxy formation model, which has been shown to be successful at reproducing many galaxy properties. And they add on top of that a subgrid modeling of the cluster population. The reason for this is that modeling the formation and evolution of star clusters directly is prohibitively expensive in terms of resolution requirements. So this cannot yet be done. So this is the best approach that we can do so far. The simulations have been shown already to reproduce the properties of young cluster populations, which are the equivalent of globular clusters but at lower redshift, and many other globular cluster observables, including the massive end of the globular cluster mass function, metallicity distribution, and also the spatial profiles as an example. And you can see here how we can zoom into one of the environments of one of these galaxies. We can capture the large scale environment. We can zoom into the detailed properties of the galaxy and its globular clusters, as well as follow it back in time and trace the formation of the globular cluster system along with the galaxy. I don't have time to go into the details here, but both the formation physics of the clusters is environmentally dependent, and their disruption and mass loss is modeled on the fly using the local tidal tensor at the position of the star particle that contains the cluster population. But of course, you're welcome to ask me more about the details later. So the philosophy of the simulations is that we want to sample across environments and not just reproduce the Milky Way, but understand the general galaxy population and the variety of environments and assembly histories. And you can see here an example of two L-star galaxies in the simulations and how different their assembly histories can be. The left one has a very quiescent assembly history, and the right one has a very, very active merger history. And the interesting thing is that the globular cluster systems across the simulation shows significant variation. And this variation has been shown to be driven by differences in the assembly histories. So this could be potentially a powerful probe of the assembly of the galaxy. And so in the first step, we simply did a comparison of the kinematics of the systems across the 25 galaxies. So here you see the velocity and the velocity dispersion components. Each galaxy is a line. So these are the radial profiles, and the black line is the median for all the simulations. And I'm also showing you the Milky Way Gaia data for comparison. And if you focus here, the first thing that you see is that the simulations span quite a broad range of kinematics, which is good news for our study. And also that typical globular cluster systems co-rotate with the stellar disk, which is a consequence of the fact that some globular clusters form within the rotationally supported disk. And furthermore, the Milky Way globular cluster system is more rotationally supported than the average galaxy, as you can see here, within the inner galaxy. And you will see in a bit why this is the case. We can further split the populations into metal poor and metal rich clusters, and we know that those trace the metallicity of the galactic progenitors that they formed this. So this is potentially also a very powerful probe of galaxy assembly. And here I'm showing you the distributions, the cumulative distributions of the ratios of the radial of the velocity components for the velocity and for the dispersion. And if we focus here on the azimuthal component, you can see that the simulations show very, very broad distributions again, and that the Milky Way, which is the vertical line, is not typical at all. Its metal-rich clusters are much more rotationally supported and dynamically colder than in the average simulation. And so if you go back to the previous slide, this again is consistent with what we already know about the Milky Way, that it had a very quiescent late merger history, such that the disk was undisturbed for a long time. So this is again, good indication that we can probe aspects of the assembly history of the galaxy. And so this is a schematic of what we're trying to do in the method. Of course, now we want to get quantitative constraints on the assembly history. And so for this, what we want to do is something like we see in the simulations. We have the galaxy merger tree at redshift 0. We have a snapshot of the rich kinematic properties of the stars on the globular clusters. This is all provided in the simulations, but of course, we want to do this with the real Milky Way. So we have the Gaia kinematics, and we want to go back and get the galaxy merger tree. But for this, we want the relation established from the simulation between the merger tree and the kinematics. So for this, we use an agnostic method where we use the kinematics and the merger trees to search for tracers blindly, sort of the assembly of the 25 galaxies. And so for this, we describe the kinematics as extensively as possible using the distribution moments of the velocities, the orbits, and the integrals of motion. And we split the globular clusters into subpopulations by metallicity and by radius, because we know that those are also powerful tracers. So we get a total of 47 tracers. Then we condense the entire merger tree into as many metrics as possible, including the redshift 0 properties of the galaxy, the halo and the galaxy growth timescales, the in situ and ex situ balance, the merger timescales, and demographics. And for this, we get 32 metrics. Then we explore the entire grid of cross correlations to find significant right-quarter correlations. And then we model each correlation between a kinematic tracer and an assembly metric using a linear model for simplicity. And so we find with this method 18 different correlations, significant correlations, but here I don't have time to get into all of them, so I'll just give you a couple of examples. We find that there's a correlation between the fraction of accreted stars in the galaxy and the interquartile range, or the spread in the orbital apocenters of the metal-rich clusters, as you can see here, such that galaxies that have a higher fraction of accreted stars have a more spread in their orbital apocenters of their clusters. And of course, this is because if you imagine the clusters coming, the metal-rich clusters coming from different progenitors and different trajectories, each individual merger is going to spread the orbits. And we also find a correlation that had not been seen in other globular cluster properties, which is quite encouraging. This is a correlation between the redshift of the last major merger and the ratio of the median eccentricities of metal-rich and metal-poor clusters, such that an earlier last major merger gives you lower eccentricities of metal-rich clusters compared to the metal-poor ones. This is a bit more complicated, but it has to do with the dynamical heating of the in situ clusters due to a big merger event and when this happens relative to the formation of these clusters. And here I also added the predictions for the Milky Way in the blue bands using the Gaia data. And you can see, again, the Milky Way is not typical. It has a low fraction of accreted stars compared to the average simulation. And it also has a high redshift of the last major merger, again, pointing to a late quiescent merger history. So like I said, we can describe 18 galaxy assembly properties in this simple exercise using only 7 kinematic tracers. So these 7 kinematic tracers are quite powerful. And we check that the predictions are in good agreement with existing constraints from other methods. And we can piece together now a quantitative, detailed history of the assembly of the galaxy, where the first period was a period of rapid growth at redshift greater than 2, where the dark matter halo, the stellar mass, and the main progenitor assembled faster than the average galaxy. It had more mergers than the average galaxy, and the last major merger happened at redshift 3, which is quite earlier than the median galaxy at redshift 1.5. Like I said, again, this is a unique prediction of this method that you cannot get from other globular cluster properties. And this was followed by a quiet history at redshift less than 2 with only 6 mergers, the last merger happening 5 gigayears ago, and this was probably Sagittarius. And about a typical number of overall mergers, relatively few major mergers, and relatively low fractions of accreted stars on globular clusters. So in conclusion, we find that the kinematics of globular cluster populations probe galaxy assembly history much more than we expected. And this is quite exciting. These correlations are caused by the effect of dynamical processes like tidal stripping and dynamical friction on the evolution of the distinct orbits of globulars that come from different progenitors in different trajectories versus the ones that are formed in situ in the galaxy. And of course, these are traced by observed kinematics of the metallicity and radial subpopulations. And of course, we might be thinking, can we do this for galaxies beyond the Milky Way? Can we understand the entire galaxy population? This is the next goal. And we've been testing, doing the same exercise with projected kinematics, which are what is available for external galaxies. And of course, you don't recover everything, but you do still recover some of the assembly features, and they agree with the 3D tracers. So this is quite encouraging again. And now we're working on extending this method to trace galaxy assembly across the entire mass spectrum in thousands of galaxies. And for this, we're using recently completed, fully uniformly resolved 34 megaparsec volume with the exact same physics of galaxy and cluster formation. This volume contains a galaxy cluster, about 3,000 resolved galaxies, and about 80 Milky Ways. So we have a huge increase in statistics, which were allow us to do this as a function of galaxy stellar mass and environment. And already quite a few interesting results are coming out of the simulation. In particular, I can highlight work by Marta Reina Campos, who is a postdoc now at McMaster in Canada. And she's about to submit a paper where she studies the spatial distributions of the globular cluster systems as a function of galaxy mass. And she finds that you can probe, using the spatial profiles of the globular clusters, you can probe the structure of the dark matter halo, both the virial radius and the concentration of the NFW profile. So even the spatial distributions carry a lot of information about the host dark matter halos. And so now we can move a little bit farther away into the local universe, into this new class of galaxies that have been pretty hyped recently, this so-called ultra-diffuse galaxies, and why they're so good at forming globular clusters. But first, why are these galaxies so special? So their story dates back to the 1980s, where some of them were found, but it was not until 2015 that the Dragonfly team built a specialized instrument and pointed it at the coma cluster that you can see in this image, and found about this 50 of these very, very diffuse smudges that you can see here on the right. You can barely see them against the background. They're very difficult to study, and you need very deep imaging. They turn out to be galaxies in the coma cluster that have stellar masses of dwarfs, about 10 to the 8 solar masses. And they turn out to have effective radii comparable to the Milky Way. So these are gigantic galaxies in that sense. However, some follow-up studies show that the truncation of their stellar distributions is actually where you expect it to be for dwarf galaxies. So this is quite interesting because it shows that these are more related to dwarf galaxies than to failed Milky Ways, as it was thought at some point. And so there was a lot of follow-up studies. A few of these studies in the following years, came up with these images. You can see all these little bright dots around these ultra-diffuse galaxies in coma. It turns out that ultra-diffuse galaxies in coma, some of them contain more than 3 times more globular clusters than normal galaxies of the same luminosity. As you can see here, this is the log axis for the number of globular clusters as a function of galaxy stellar mass. Normal galaxies are here in green and in gray, and the ultra-diffuse are colored color bars. And so you can see some of them are extremely efficient at forming globulars. And this is, if you can see what I'm getting to, this is quite puzzling because these galaxies are some of the lowest density stellar systems that we know of, whereas globular clusters are some of the highest density stellar systems. And globular clusters require very high gas pressures and densities to form. And so it's really difficult to see how these two could come together and these two could be related. And so this got us very interested into these galaxies. And then some studies later on of the now infamous NGC 1052 group of these two galaxies, DF2, DF4, by the same Dragonfly team. They seem to be pretty normal ultra-diffuse galaxies, except that when looking at their globular cluster populations, it turned out they have more globular clusters than normal, which is also known for other UDGs, but their globular clusters seem to be 4 times more massive than in other galaxies. So in other galaxies, globular cluster seems to have a universal mass function that peaks around 200,000-300,000 solar masses, and it has a log normal shape. This was the first 2 galaxies where it was seen to differ from this shape. And so with globular cluster masses that are typically exceeding 1 million solar masses. So the mass of an entire galaxy. And of course, this was heavily contested. Many papers argued that this was due to systematics in the determination of the distances. However, this result seems to hold up. The distance seemed to be confirmed where the initial studies predicted it about 20 megaparsecs. And then if you look at what a normal dwarf toroidal galaxy would look like if it had this kind of globular cluster system, you see how dominant the light would be. So this also made us think like, maybe the globular clusters are not simply passive tracers of the galaxy formation, but they're actually influencing it. And you'll see where this takes us to in the next project. But these further studies of the dynamics of the globular clusters and the stars from different groups shown to the surprise of many people that these galaxies can be explained without dark matter. Basically, their kinematics are consistent with just containing stars. And of course, this caused even more controversy. There was a lot of debate about the distance and how it affects this result and how the measurement of the kinematics affects the result. But again, it seems to hold up. And the latest chapter in this debate about the distance came earlier this year, where Sebastian and collaborators used 40 orbits of HST to get the deepest imaging of these two systems to date, and to really get a precise determination of the relative distance, which is now 2 megaparsecs. So they're not in the same galaxy group, surprisingly. So at least one of them has to be, one of them is a dark matter deficient galaxy that is isolated. And this is a huge problem for galaxy formation models, which try to explain the dark matter deficiency in these galaxies through tidal stripping in high density cluster or group environments. If the galaxies are isolated, you might need to resort to an intrinsic process to get rid of the dark matter if you're still doing it in the context of CDM. And things got even more complicated when people looking at galaxies in the Alfalfa blind H1 survey identified some galaxies that seem to be rotating very slowly for their given baryonic mass. So in other words, they're offset from the baryonic Tully-Fisher relation, this stars right here. And they got rotation curves of these galaxies, and they determined that their dark matter halos are very, very low mass. They're also consistent with being explained without dark matter. And these are definitely isolated galaxies. These are also UDGs, but they have a lot of gas and they're star forming. So there seems to be a common theme between these galaxies, and maybe a new population of galaxies that we're just beginning to probe, galaxies without dark matter. And so going back to DF2 and DF4, we were thinking about the globular cluster mass function and how to explain this. The problem is that in the typical assumption for the initial cluster mass function of star clusters, there's not enough mass in the entire galaxy to have formed the globular clusters this way. So basically that constrains, that tells you that the initial cluster mass function has to be environmentally dependent. So we put together a very simple model based on galactic environment and feedback and how this regulates star cluster formation. And in this model, we predict that the globular cluster, the initial cluster mass function is a Schechter function with a truncation at low and high masses that are environmentally dependent, and a sort of universal logarithmic slope of -2, which is set by the hierarchical nature of molecular clouds. And then the predictions of this model can be summarized in this plot here in the parameter space of angular velocity, which is a probe for the density of the galaxy, and versus galactic gas surface density. And you can see that both the minimum and the maximum cluster mass vary orders of magnitude across observed galaxies, going all the way from nearby galaxies in the solar neighborhood to high redshift galaxies, which are here, and to starbursts and the center of the Milky Way, which has quite extreme conditions. And also the width of the cluster mass function can vary a lot. So you can get very broad mass functions and very narrow mass functions, as in the case here of the center of the Milky Way. And we indeed made predictions for observed cluster mass functions, which seem to agree with what the data that we currently have available for the solar neighborhood M31. And interestingly, for the center of the Milky Way, it predicts the model predicts a very narrow mass function, which is indeed apparently what is observed. And so here's the solution that we get from, so using this model, we can simply invert it. We can do archaeology of the globular cluster mass function and find the star forming environment that produced it. And this is the solution right here. So we see that the initial cluster mass function had an initial mass that was rather high compared to the solar neighborhood, which would be around here. And these are the conditions that produced it. So the galaxy had very high gas surface densities and very high angular speeds or shear. And so the F2 had extreme star forming conditions of redshift greater than 1. This is not so extreme if you look at dwarf galaxies at that redshift that seem to be rather common. But it contrasts with the nature of the galaxy at present. And just to show you how much the galaxy must have evolved, these are the current constraints on the mass distribution of the F2. And this is what the cold gas at redshift greater than 1 looked like, the one that formed the globular clusters. And you can see that the galaxy must have expanded more than a factor of 20 between then and now. We also concluded that because there's no nuclear cluster, that a major merger rather than a starburst could have been the likely origin of the massive clusters. And of course, but this begs the question: what caused the expansion of the galaxy? We still don't know. And so this leads us to the next project. So to conclude this part, we find that galactic environment shapes globular cluster populations, that the overabundance of massive clusters is the result of high pressure and shear cosmic noon, and that they point to very compact progenitors of UDGs at high redshift that expanded dramatically. So we can begin to probe the formation of these galaxies. And the questions are, does feedback from cluster star formation possibly affect the structural evolution of the galaxies? And could globular cluster feedback explain the observed lack of dark matter in some UDGs? So we think maybe this could be related. And so to understand this, we put together the simplest possible galaxy evolution model that we could think of, starting from this fundamental relation, the stellar mass halo mass relation that relates galaxies to their host dark matter halos. You can see it here exemplified by the halo abundance matching result. It can be constrained from many other probes, and they all sort of agree, especially at the high mass end. But as you can see here in the dashed line, the constraints stop because current surveys are not deep enough. Here you can see in the gray is the observed scatter in the relation, and in black the mean relation. I'm also showing the cosmic baryon fraction, which is the budget, the baryonic budget of galaxies, about 15% of the halo mass, and the line of equality between the stellar mass and the halo mass. However, once you put in direct constraints on the masses of the halo masses of observed galaxies, the situation gets a bit more complicated. You can see that there's a lot of scatter despite the large error bars. Here I'm showing you the spark sample and some nearby dwarf irregular and dwarf spheroidal galaxies for which we have mass models. And then if I add some additional data from the last few years for very peculiar galaxies, including DF2 and DF4 here in the stars, and the pentagons or the gas-rich UDGs that I mentioned earlier, also these green triangles or some alpha-alpha galaxies, you can see that they begin to cross into this forbidden zone where galaxies should not form. If I add the gas content of these galaxies in this relation and I plot the total baryonic mass, they would actually be even more into the forbidden zone. So this led us to believe that maybe the scatter in this relation is much larger than we thought. And we built a model for galaxy evolution based on the basic premise that the scatter in stellar mass at fixed halo mass correlates with the assembly timescale of galaxies. And this is not such a crazy assumption to make. This correlation has been observed to emerge naturally in big hydrodynamical simulations like Illustris TNG, and Eagle. So at fixed halo mass, halos with earlier collapse times that formed earlier have larger stellar masses. And this is explained by the fact that they have more time to form stars and they have deeper potential wells, so they're more efficient at converting gas into stars. So we started with this assumption and we built the model, and I'll walk you through the steps of building this model. First, we choose a halo mass and the allowed scatter around the mean relation. We limit it up to the cosmological baryon fraction, following what we kind of see in the observational constraints, and then we get the allowed range of stellar mass. Then we assume that the stellar mass halo mass scatter correlates with halo concentration, such that earlier collapsing halos have larger M star, like I said before. And this is the relations that you get. Since we know that in CDM concentration is a direct probe of collapse redshift, these two are similar. And you can see that low mass dark matter halos collapse earlier, as we know, as predicted by simulations. And also, as you scatter above the relation, you have earlier collapse. And this assumption here that we're making is rather weak. And then you can completely determine the galaxy properties at the collapse redshift. You can use the empirical relation between the effective radius and the real radius to get the initial size of the galaxy, and then assume that a fixed fraction of the total stellar mass formed at that epoch. In this case, we assume 20%, and then obtain the gas properties using, so we have the star formation rate, the surface density of star formation, and then since we know that Kennekrich-Schmidt holds at high redshift, we can get the gas surface density. And once we assume exponential gas and stellar profiles and NFW for the dark matter, we completely specify the mass profile. And these are the results. As expected, the star formation rate goes up as you scatter above the relation. A huge increase in the surface density of star formation and in the gas surface density. So you can see where I'm getting to. These are the conditions that you need to form massive clusters.
Can I ask a quick question?
Yes, of course.
Can you go back?
Oops.
Yeah, so in those plots,
yes,
the color scheme, for example, gives the concentration or the collapse redshift, but we have no idea on the actual histogram of the halos. So, you know,
yes,
if 99.999% of the halo are sitting very close to the black line,
that's true.
It's completely different than where you know, the case where halos are uniformly distributed in this colored region here, right?
No, I'm not assuming a distribution. This is information that we don't have in the model. So I'm simply assuming if you have a certain deviation in concentration, but remember that, but remember that here we're only going, if you move vertically, you're still at the same halo mass. And
no, I'm just saying that there is no information on the actual statistics, right?
Yeah, that is correct.
If you go to the previous plot, the observed yellow above matching, there is a dark gray band, which, according to the authors, indicates where 66 or 90% of the galaxies are. Right?
It
means that all these other galaxies are very rare.
So the problem is that the halo abundance matching result is based on surveys, right? And surveys do not typically have these kind of galaxies. This is why these galaxies are so hyped now, because they were not in previous surveys like Sloan. They're not in Sloan. Sloan is not deep enough. So if these galaxies are absent, then you don't have the statistical constraint.
No, that's true. That's true. But still, even if, let's assume we see all the galaxies in the universe, we still, need to agree on the statistics, like how many galaxies you have per dex above and below the black line, right?
Yeah.
Sorry to interrupt.
And this is something that would be useful to constrain, of course. Yeah, I agree. So going back to here, then, since we have the full mass distribution of the galaxies, we can assume a hydrostatic equilibrium disk and the cluster formation model that I described earlier to fully specify the fraction of stars that are forming in bound clusters and the cluster mass function. And then we can predict the number of globular clusters, for example. And so this is the fraction of stars in bound clusters. As you see here, it goes in normal galaxies on the relation from about 10% or slightly above, all the way to 100%. So galaxies need the cosmic Merriam fraction in this model can turn all their stars into bound clusters. This is quite extreme. And also because of the shift in the initial cluster mass function, the mean cluster mass increases by several orders of magnitude. So not only more stars are in bound clusters, but they're also in more massive clusters. And this is exactly what we see in some of these observed UDGs. We know also that the clustering of feedback is very important for the efficiency of galactic wind production. This is from detailed hydrodynamical simulation. So we can use a model derived from the simulation based on the clustering of the supernova that we have from the cluster demographics. And then we can predict the energy loading of the galactic winds. And this is what it looks like. Again, as you go up from the relation, you get a huge increase in the clustering of the supernova because you have the population of stars is dominated by massive clusters. And then this drives a huge increase in the wind energy loading to the point where if you're close to the cosmic baryon fraction, you have 100% of the supernova coupling to the galactic winds. Then we can assume, we need to assume the fraction of the wind energy that goes into modifying the potential so that it can inject energy into the orbits of the dark matter particles to predict the dark matter halo core size. This is a rather conservative assumption compared to what simulations have shown. And then we can use the core NFW model, which is based again on hydrodynamical simulations, to relate the formation of the dark matter core to the expansion of the old stars. And we simply assume that the young stars are not expanded for simplicity. And we combine the two stellar populations, and then that fully specifies the distribution of stars and dark matter at redshift 0. So that's the model for you. And then we can make some predictions with this model and compare them to observations. So we find that galaxies above the mean relation form larger globular cluster populations. If you can compare this here to some observed dwarf galaxies for which we have globular cluster counts, and you can see there's a rather weak trend with a lot of scatter in the observations in this color bar of increase as you go towards larger stellar masses of fixed halo mass. We sort of, this trend is sort of reproduced qualitatively in the model, so that is quite encouraging. And we predict that the overabundance of globular clusters has a strong effect on the expansion of the galaxy. This is the size of the dark matter core and the effective radius of the stellar component. And here I'm highlighting the region where UDGs are typically observed. You can see that the biggest effect is exactly where this region is. So galaxies near the cosmic baryon fraction will get extremely expanded, and we'll get very large dark matter cores. And then if you look at the dynamical mass to light ratio, you see that these galaxies have completely or almost completely explained with our dark matter. But there's enough variation of about a factor of 50 to 100 in the dynamical mass to light ratio. And this is important because some UDGs actually seem to have their normal amount of dark matter. So you need to explain this variation. Then we looked at what's driving the expansion. This is the comparison between the wind energies in the fiducial model versus a model with no clustering of supernova. And we see that most of the expansion, most of the wind energy is coming from the clustering of the feedback, and also the effect on the size of the dark matter core and the galaxy effective radius is due to the clustered feedback. And so finally, just before I finish, we can go back and revisit this pathological galaxies, DF2, DF4, and the gas-rich UDGs. So I'm just going to show you the example for DF2 and DF4. We can predict the detailed mass distribution. So here I'm showing you the amount of dark matter within 10 kiloparsecs, within 8 kiloparsecs. As you can see, once you cross this ridge here, you begin to lose a lot of dark matter because of the effect of clustered feedback. This is the stellar mass range of these two galaxies. And of course, we don't know the halo mass. So we can try different positions in this diagram. If you try it here on the relation, as before, we see that the halo mass is too large. Even with a dark matter core, this is not even close to the constraints, the observational constraints. This is the circular velocity. And then once you get a bit above the relation, if you assume that this galaxy scatter upwards and it's close to the cosmic baryon fraction, then the fact that you have a lower mass halo, which is about 10 times lower mass, and also very strong effective feedback can bring the dark matter density into agreement with observations, and the baryon fraction goes up. We did the same thing for the gas-rich UDGs, and we also get reasonable agreement. So So we think that this is quite encouraging for such a simple model. Yeah, like I said, this is the results for the gas-rich UDGs, but I won't get into the details here. And to conclude, we find that galaxies that lie above the mean stellar mass-halo mass relation in the model formed earlier with higher gas and star formation rate densities, they form more globular clusters and more massive clusters, are much more effective at launching galactic winds due to the clustering of feedback from the globulars, and evolve into isolated UDGs driven by the expansion of the stars due to the globular cluster feedback. And the combination of the scatter and the stellar mass-halo mass relation and globular cluster feedback leads to a large diversity in dynamical mass-to-light ratios. And galaxies near the cosmic baryon fraction can grow very large cores and evacuate most of their central dark matter. And this fits the dynamical constraints for some of these very strange dark matter-free galaxies that have been found without the need for eccentric orbits and high-density environments. And this is key because these galaxies are isolated. And we believe that it seems, at least in the model, globular cluster feedback seems to be such an important ingredient that it should be included in hydrodynamical simulations to fully capture the galaxy diversity that we see in observations. And this is, of course, the next step that we're going to take. Thank you very much.
Thanks a lot, Sebastian. Am I supposed to initiate the question round? Okay. Okay, so here we go. If anybody has questions, please either speak up or
I have a question,
or write it in the chat or whatever.
I have a question, but I must apologize. I missed the 5 or 10 first minute of the talk. Maybe you discussed this already, but I'm curious about how you define or you detect and define globular clusters in this cosmological simulation that you showed at the beginning.
Yeah. That's a good question. I didn't have time to get into the details. So this is what you see. Yeah, this is this movie here. So, so the simulations use the Eagle galaxy formation model. Because these are rather big simulations, the resolution is not too high, and the clusters are a subgrid model. So in each star particle, you divide the stellar mass into a clustered component of star formation, according to that model that I showed you for the bound fraction, and then you put that into an initial cluster mass function that you sample statistically, and then you get a population of clusters. It's the same model that I described in the later slides, where the initial cluster mass function and the bound fraction both depend on galactic environment. So at high redshift, the high pressure conditions of the ISM lead to more massive clusters. And at low redshift, you get lower mass clusters, as you see, for example, in the Milky Way. The Milky Way is not currently forming globular clusters. I actually have a slide about this. Yeah, these are the physical processes that are included, the physical ingredients are included. Like I said, the cluster formation efficiency, the mass function, and then mass loss by stellar evolution, tidal shocks, and evaporation, using the evolving local tidal field of each stellar particle. So it's calculated at each time step, and then you calculate a mass loss. And then in post-processing, you throw away the clusters that are supposed to spiral into the center of the galaxy. So these are, yeah, so these are not real clusters. These are a subgrid population.
Oh, thank you. Very clear. Thank you.
Okay, Robert.
Hi, well, great talk. I have a couple questions. And I don't know whether I can ask them all now because I don't want to take up all the time. But okay, so the first one, maybe it's like a simple one, but I think it's an important one. So, so one of the things that I get a little bit is that you have a range of models which have like very reasonable assumptions, but unfortunately, many of the assumptions are also uncertain. So you know, and then you so make predictions for the observations we have, and it works, and that's good. What I wonder about is, like, have you actually predicted or made any predictions for like for observational tests that are yet to be done, that we can actually check how well these models actually work on something we don't know yet? So for instance, I was wondering, let's say about metallicities, right? So you would, I think, also be able to make some predictions for the metallicities or abundance ratios in these galaxies, I suppose.
Yeah, of course. So I didn't have time to show all the results that have come out of the simulations. There's quite a few papers looking at different aspects. And yes, it's extremely difficult to know whether your model actually is doing things right. I mean, this is the question that we all have in simulations, right? But I think it's been tested enough that, you know, if you reproduce the way that old globular clusters look like in terms of their mass, their metallicities, we also reproduce the blue tilt, which is the dependence of color, globular cluster color on galaxy mass, which tells you how globular cluster formation varies from dwarf to massive galaxies. Also the spatial distributions and a few others that I can't think of right now. These all seem to work rather well. Oh yeah, in the last paper, Megan Hughes looked at the truncation mass of the mass function as a function of stellar mass compared to data that we have for the Virgo cluster. Of course, this is all data that exists. These are not technically predictions, but of course the observational data did not go into tuning the model. So the physics of the model is rather simple and was not and is not tuned based on the observations. And there's such a variety of observations that leads me to have trust that the model is doing at least some things well. Of course, there's predictions with the new volume that I mentioned. We can predict things. We have a student working, for example, on the correlation function of globular clusters. So similar to what you do for galaxies, you can do this for globular clusters in probably with surveys like LSST, and how this relates to stars. So this is a prediction that has not been measured yet, that has not been observed. I can't think of many others, but I think this field is really going to blossom with the new facilities, because we're going to be able to characterize a lot of globular cluster systems in nearby galaxies. And yeah, then there's also whether you, I think the luminosity functions of the globulars as a function of redshift. That is another prediction that you can make.
Okay. Actually, I had another question that was related to this simulation. So because you just kind of super briefly mentioned it, is this essentially like, again, the same thing like Eagle physics, but or is it something different? Because it's a smaller volume than Eagle, so I assume you did something different here, right? In this box.
No, it's the same physics. It's actually slightly larger volume than the highest resolution volume of Eagle, which was 25, I think.
Oh, so you compare with, okay, so that's why. Okay, so it's the same. Is it higher resolution than the Eagle one?
Yeah, sorry, it's the recall physics, if you're familiar with this. So it's the physics that gives, I think it's, yeah, actually I'm not sure if it's slightly different from the lower resolution bigger boxes, but yeah, it basically gives you the same galaxies. We're just adding the star clusters on top, basically.
Okay, and the physics, well, the modeling approach that you did is essentially kind of the same as what you presented in the beginning of the talk, right? It's just a different volume.
You mean for the analytical model?
Yeah.
Well, it's a much simplified version of this, of course, because we're assuming that galaxies form at the collapse time, and that they form a lot of the stars in one burst. So it's a really kind of simplified model of galaxy formation that is simply designed to test whether globular clusters could have a strong impact on the evolution of the galaxy. But to make really quantitative predictions, I think we need to put this into simulations, which is the next step.
Okay, thank you.
Thanks.
Okay, Joachim?
Yeah, so my question was a little bit related to Robert's. And so you mentioned that some of these galaxies are rare and they haven't appeared in surveys such as Sloan so far. And I was wondering what implications would this have for Euclid observations, and that is for the wide, and also there's a deep survey which will presumably see many of these galaxies. Have you looked at, made some mocks for Euclid that would, would you see these galaxies, or how many would you get, and things like that?
Yeah, that's an excellent question. You just scooped one of my ideas that I had for follow-up of this. Of course, like I said, it's a very simple model. So you got to take predictions with a grain of salt. It's more qualitative, but I think one of the things you can do is just convolve it with the statistics. You have to assume some kind of statistics, but there's already some evidence from studying UDG populations of how big of a percent it is. And so some people estimate that they're like about 10% of the galaxy population. However, this only applies to the ones that you can see again. And like I said, these are 10 to the 8 solar masses. There's not so much evidence of UDGs of lower masses, but perhaps again, this is because we cannot see them. So it's very expensive to do surveys to get these populations in volume limited samples. But I was thinking that you could make some predictions for this, and it would also be interesting and tie back into the question of the missing dwarf problem, which is something that I worked with Aurel on when I was here at the Institute. And it has to do with whether we fully know how many galaxies there are as a function of stellar mass. So yeah, I think all these surveys, including LSST and I guess Euclid as well, and also the blind H1 surveys are going to be super useful for testing these things. Yeah.
Yeah, that's very interesting. The other question that I wasn't quite clear on was, you have the model at the end, the semi-empirical model, and you have simulations at the beginning, which you discussed. And are the extremely off the relation galaxies that you have in your semi-empirical model, do they appear, do you get them in the simulation as well, or are they, do you need a bigger volume to get them? They're kind of related questions.
This question, that's a good question. It has been haunting me. And I was waiting for the time when somebody would ask me this question, because I don't think they show up in this, from my understanding. I think the scatter in the big box simulations is smaller and closer to what you predict from halo abundance matching. And I've been thinking a lot about whether this is actually because of the way that the simulation physics was tuned to reproduce the stellar mass halo mass relation. I guess Robert agrees with that. he's nodding. But although I don't know, I guess you could compare also to zoom in simulations, but then it's harder to constrain the scatter. But I think this is one of the things that the next generation of hydro simulations should focus on, not just reproducing the average galaxy, but to understand what drives the scatter. And a lot of people have studied how chaos is important in simulations. So it is very complicated, because you can run a simulation twice and you get a different galaxy with the same initial conditions. So yeah, I think either the observations have severe systematics, or we're missing the scatter in the physics. There's something in the physics that drives the scatter. And it could be related to how the feedback cycle, star formation cycle, regulates the assembly of the galaxy. Maybe the way that it is tuned in the big box simulations tends to narrow this. If you look at fire, these things are exploding, especially at dwarf scales. And so you would expect that there's there's a lot of scatter from the way that feedback is, but how, of course, feedback is one of the hardest things to understand empirically. So.
Okay, thanks very much.
Thank you.
Okay, I don't see any other question. I think we are way above time already, so I think we can stop this. Sebastian is at the Institute. For those who are here and have further questions, they can come. We're going.
I'm going to be here all day, so if anybody wants to chat, I'll be around for coffee or whatever is allowed.
Okay, great. Thanks a lot, Sebastian.
Thank you guys for inviting me.